This presentation would be meaningless to you if you don't know what differentiation is, so study, then come back and listen to this. Introduction. In geometry, you know how to find the area of basic shapes, such as circles, squares, rectangles. For example, the area of a circle is pi r squared. The area of a square is a square of its sides. However, if the shape that you want to find the area of is non-regular shape, like the area under the sine function, you cannot use a specific formula. Integration allows you to find the area underneath a function. You can do this by taking a tiny segment, dx or dy, to find the area of this segment. We can assume that this segment resembles a rectangle. If you choose infinite tiny segments, calculate the area of each of these segments, and then add the area up, you'll get the total area underneath the curve. This is the point of integration and why we integrate. Integration is the inverse operator of a differential operator. So in order to do integration, you have to be well versed in at least the basic differentiations, because when you take an integral of a function, you end up with the antiderivative of that function. Chapter 5, Integration. In this chapter, we will learn some different techniques about solving some integral problems. Basically, integral operator is the inverse of differential operator. So we'll be using this to help us out. We have here a list of 9 techniques. We have basic integration, use substitution, trigonometric identities, integration by parts, trigonometric substitution, partial fractions, completing squares, root elimination, and sine and cosine elimination. These will all be utilized to help solve integrals. We have here a basic integral. Just need to use this table for basic integration that you must know from your 1A class. And here's a list of some basic integrations. Notice that the antiderivative listed on this table have a plus c at the end. This is because integration is memoryless. This is the key difference between integration and differentiation. When you take a differentiation of a function, any constant is reduced to 0. This means that, for example, you take a differentiation of y equal to x squared plus 6, or y equal to x squared plus 290, you would simply get y equals 2x. The differentiation of both of these functions is the same. If you integrate y equals to 2x, you get y equals x squared plus any constant, which is why we add the plus c. Integration of y equals to 2x can be y equals x squared plus 6 or y equals x squared plus 290. So the c accounts for the inaccuracy of the memoryless characteristic of integration. Technique 2, use substitution. This method can solve integration problems in 2 ways. Either change the problem into a basic integral or change into another integration that can be solved by another technique. Use substitution makes the function easier to integrate by spotting a basic integral inside the seemingly complicated integral. You will see that this is usually the theme for all the techniques we will cover. Today we're going to be doing a simple use substitution. The integration will go from 0 to ln of 3 of e to the 3x dx. First we'll set u equal to 3x, which would mean that du will equal 3 dx. Switching this around, we can then have du over 3 equal to dx. Plugging this back in, we'll have the integration of e to the u over 3 du. Pulling out 1/3, we'll have 1/3 the integration of e to the u du, which will simply be e to the u over 3. Plugging u back in will give us e to the 3x divided by 3, integration range going from 0 to ln of 3. This will give us e to the 3n of 3 divided by 3 minus e to the 0 divided by 3. This simplifies to 27 thirds minus 1/3, which is 26 over 3. Now we're going to be doing a harder integration involving u substitution. We have the integration of dx divided by the square root of x plus 1. Using u substitution, we can then have u equal to the square root of x, giving us 2u du equal to dx. This gives us the integration of 2u du divided by u plus 1. Using more u substitution to simplify the integration, we can have m equal u plus 1, which means dm equals du, where m minus 1 will equal u. Rewriting the integration again gives 2 times the integration of m minus 1 divided by m dm. Simplifying this integration, we will have 2 times the integration of m over m minus 1 over m dm. We can then integrate, which will give us 2 times the quantity m minus ln of m plus c. Simplifying this further, we will have 2m minus 2 ln of m plus c. However, we need to then put m back into the equation as u plus 1. This will give 2 times the quantity u plus 1 minus 2 times ln of u plus 1 plus c. However, the original equation is in terms of x, so we then need to plug in x into the equation as u equals the square root of x. This will give us 2 times the quantity square root of x plus 1 minus 2 times ln of square root of x plus 1 plus c. This will be our final answer in terms of x. Technique 3, Trigonometric Identities. It's important to review your trigonometric identities because they will be utilized for integration. It's also important to review your hyperbolic functions because those will also be utilized when trying to solve integral problems. Specifically, if we have the integration involving a cosine and a sine, or involving the integration of tangent and secant, there's different techniques that will be helpful to solve these integrations. If we have the integration of cosine and sine, there's 3 different ones that will be important. We have, if m is odd, we'll save one of our cosine x as our du, that way we can integrate in terms of u. If n is odd, then we'll be saving one of our sines as our du, that way we can integrate in terms of u using cosine x. If both m and n are both even, then we'll be using half-angle identities to simplify the integral. So it's important to review those and know them. If we have the integration involving tangent and secant, if m is odd, then we will save one of our secants and one of our tangents to set as our du. That way we can integrate in terms of u equal to secant. If n is even, then we'll be saving 2 of our secant squares to set as du. That way we can integrate in terms of u. If m is even and n is odd, we'll be using other identities to simplify and then integrate term by term. This table here is helpful if you have an integration in terms of the box that's labeled in this expression. You'll be using trigonometric functions to set your x equal to. That way you can use trigonometric identities to simplify your integration. This will be helpful, so make sure you review this as well. We're now going to do a harder integration involving trig substitution. We have the integration of x cubed dx divided by the square root of x squared plus 4. We can simplify this a little bit more to integration of x cubed dx divided by the square root of x squared plus 2 squared. We can then set x is equal to 2 tangent of theta. dx then will equal 2 secant squared theta d theta, but it will be helpful if we set tangent theta is equal to x divided by 2. We can then plug in these values into the integration, giving us the integration of 2 tangent theta cubed times 2 secant squared theta d theta divided by the square root of 4 tangent squared theta plus 4. Now we're going to do a little factoring and simplifying here. So we're going to write it in terms of integration of 8 tangent cubed of theta times 2 secant squared theta d theta divided by 2 secant theta. We can then simplify and cross out some terms, which will give us the integration of 8 tangent cubed of theta times secant theta d theta, which will simplify to 8 times the tangent theta secant theta times secant squared theta. Now this will be important for when we simplify, because tangent squared theta will equal secant squared theta minus 1. We can then simplify and write that out as 8 times the integration tangent theta secant theta times the quantity secant squared theta minus 1 d theta. We then will use a little bit of u substitution. Let me write that out real quick. Oh, sorry. Erase that and rewrite. So we have u is equal to secant theta, where du will equal secant theta tangent theta. And that's going to be important for the simplifying. So we have the integration, 8 times the integration of the quantity u squared minus 1 du. Now we can just integrate this term by term, which will give us 8 times the quantity u cubed divided by 3 minus u plus c. Now we need to put back in terms of theta, so we have this part right here, adding the plus c at the end. Now, because we have secant theta, we need to draw a triangle so that we can determine what that is. So we have our theta angle down here at the bottom. Square root of x squared plus 4 off to the top here, with 2 down at the bottom and x to the side. We then need to find what secant theta is. So secant theta in terms of x will equal the square root of x squared plus 4 divided by 2. And we will need to put that into the original equation and then simplify, which I'm doing right now. And then this will give us the final answer in terms of x. Technique 5, integration by parts. What if the integrand is neither basic nor composite? What if the integrand is a product of 2 functions? In this case, we would use integration by parts. If you let one function be equal to u, another function be equal to dv, you will then differentiate u and integrate dv. So we'll use a kind of a manipulation of the product rule, which will give us our main formula for integration by parts. We have the integration of u dv as equal to u times v minus the integration of v du. Now it's important to have that very clear in your head because it will be used when doing integration by parts. If you have, as an example, the integration of f of x times g of x dx, we would then let u is equal to big F of x, and our dv value will be equal to little g of x dx. We then will differentiate u, giving us du is equal to little f of x, and we will integrate v, giving us big V equal to big G of x plus c. We then would plug these values into the integration, so we'd have the integration of f of x times g of x dx as equal to big F of x times big G of x minus the integration of big G of x times big F of x dx. It's also important to note which order that you would choose u in. So we have the top inverse functions. We would then have polynomials next. Exponential and sinusoidal would then follow, with d of x being the last option. Now that we've learned how to do basic integration by parts, let's do an easy example. We'll have the integration of x sine x dx. Using what we've learned, we can then set u as equal to x, giving us du equals dx. We then will set dv as equal to sine x
dx, which means v will equal negative cosine x. Putting in our arrows to help us out for rewriting will give us the integration of x sine x dx as equal to negative x cosine x minus the integration of negative cosine x dx. Now we can rewrite this as negative x cosine x plus sine x plus c, which will give us our final answer. Now that we've done an easy integration by parts, let's move on and do a little bit more difficult one. We'll have the integration of ex sine x dx. We'll set u is equal to ex, which gives us du is equal to ex dx. dv will equal sine x dx, giving us v equals negative cosine x. And put in our arrows will give us negative e to the x cosine x minus the integration of negative e to the x cosine x dx. Now recognizing we've just put ourselves into another integration by parts, we'll set u is equal to ex, giving us du is equal to ex dx, putting dv as equal to cosine x dx, giving us v as equal to sine x. We can then rewrite the whole integration as the integration of e to the x sine x dx as equal to the negative e to the x cosine x from the first integration by part plus e to the x sine x minus the integration of e to the x sine x dx. Now recognizing that this just gives us our original equation again, our original integration, we can add it to the other side, which then gives us 2 times the integration of e to the x sine x dx as equal to negative e to the x cosine x plus e to the x sine x. We simply then need to divide by 2 to both sides, which will give us our final answer. Technique 6, partial fraction. A method of partial fraction, like the other techniques we have done so far, helps us simplify the integral. You've actually learned this technique of partial fractions before in previous classes, and if it's not familiar, you should go back and review. This technique breaks down the integrand into simple integrants so that you can integrate it term by term. This is very important when we're doing integrations to try and simplify as much as possible, and this technique will definitely help with that. There are some important notes though. Number 1, if the degree of x is not lower than the degree of x in f of x, we need to use long division to obtain the proper form. This will mean that the degree of the polynomial in the numerator must be less than the degree of the polynomial in the denominator. Number 2, we need to express x as a product of linear factors ax plus b or irreducible quadratic factors such as ax squared plus bx plus c, and then collect the repeated factors so that x is a product of different factors of the form the quantity ax plus b times n to the n, or the quantity ax squared plus bx plus c for a non-negative integral to the n power. Number 3 is also very important. We need to apply the following rules, where for each factor of the quantity ax plus b to the n, with n greater than 1 and with the quantity ax plus b being irreducible, the partial fraction decomposition contains a sum of the n partial fractions in the form of the following box, where you have a divided by the quantity ax plus b divided by the quantity ax plus b squared to the nth term. For each factor where you have the quantity ax squared plus bx plus c to the n, with n greater than 1 and with the quantity ax squared plus b plus c being irreducible, the partial fraction decomposition contains the sum of n partial fractions in the form of ax plus b divided by the quantity ax squared plus bx plus c to the nth term as well. The power of the numerator needs to be always smaller than the power of the denominator, which is a very important step. It will be important to review techniques such as Heaviside method when solving for the values of a and b. We will be doing that in the following examples, so if none of this makes sense to you, you should probably go back and review partial fractions. We'll now be doing an integration using partial fractions. We have the integration dx divided by x squared minus 1. Rewriting this, we can have the integration of dx divided by the quantity x plus 1 times the quantity x minus 1. We can then rewrite this using the quantity a over x plus 1 plus b over x minus 1. We can then rewrite as 1 equals a times the quantity x minus 1 plus b times the quantity x plus 1. Simplifying, we can then have 1 equal ax minus a plus bx plus b. Separating out like terms, we can have 1 equal x times the quantity a plus b plus b minus a. Oh, sorry, wrong color. We read that in red. Okay. We now can set a plus b as equal to 0 because on the left-hand side we have a 0x in front. We can then write b minus a as equal to 1. Now simplifying this, we can add the two terms together, which means we can cross out the a's, which leaves 2b as equal to 1. Giving us b equals 1/2. Rewriting the equation, we can write a plus b as equal to 0, which gives negative b equals a. Plugging it in, we can then find that a will equal negative 1/2. Going back to the original integration, we can rewrite the integration as the quantity negative 1/2 over x plus 1 plus 1/2 over x minus 1 dx. Integrating separately will give us negative 1/2 ln of the quantity x plus 1 plus 1/2 ln of the quantity x minus 1. And this will be our final answer, plus c. And this will be our final answer. We're now going to be doing an integration using partial fractions. The integration is 2x plus 1 divided by the quantity x times x plus 1 times x plus 2. Separating this, we can then have a over x plus b over x plus 1 plus c over x plus 2. Using lowest common denominator, we can then have 2x plus 1 equals a times the quantity x plus 1 times the quantity x plus 2 plus b times the quantity x times x plus 2 times c times x times the quantity x plus 1. Using Heaviside method, we can then have x equals negative 1, which will result in b equaling 1. Using x equals 0, we will then find a as equaling 1/2. And using x minus 2, we can then find that c will equal negative 3/2. Plugging this back in to the equation a over x plus b over x plus 1 plus c over x plus 2, we will then have 1/2 over x plus 1 over x plus 1 plus -3/2 over x plus 2. We can then integrate this term by term, which will result in 1/2 ln of x plus ln of x plus 1 minus 3/2 ln of x plus 2 plus c, which is our final answer. Technique 7, completing the square. In this technique, we need to use a method that we learned in algebra called completing the square. This method turns an unfactorable polynomial into a factorable form. The first step that we have for completing the square off to the right-hand side is factoring out any a value that you have. You then need to add and subtract your b squared divided by 4a squared. That way you're not changing the equation. You can then factor this a little bit more, giving a simplified version. The benefit of completing the square will become more apparent once we look at problems where this method is required. However, if it's not clear to you, you should go back and review your algebra. We're now going to be doing another integration involving completing the square and trig ID. The integration is dx divided by x squared minus 4x plus 5. Adding 1 and subtracting 1 in the denominator will give us the integration of dx divided by x squared minus 4x plus 4 plus 1. Completing the square will give us the integration of dx divided by the quantity x minus 2 squared plus 1. Using trig ID, we can then set x minus 2 as equal to tangent theta. This will mean that dx will equal secant squared theta d theta. This can then be plugged back into the original equation, giving us the integration of secant squared theta d theta divided by tangent squared theta plus 1. Now, because secant squared theta is equivalent to tangent squared theta plus 1, this simply gives us the integration of d theta, which is equal to theta plus c. Now, plugging it back in, we get this as the final answer. We're now going to be doing a harder example using completing the square. We have the integration of dx divided by 2x squared plus 4x minus 3. Down in the box, we have our plus 1 subtracting 1 for completing the square, which gives us 2 times the quantity x plus 1 squared minus 5. We can then use this in the integration to simplify a little bit. It gives us 1/2 times the integration of dx divided by the quantity x plus 1 squared minus square root of 5 over 2 squared. We can then use u substitution, where we let x plus 1 equal the square root of 5 over 2 secant theta. We can then use this to rewrite the integration in terms of theta. Let me write that out real quick. We can then simplify, which leaves us with 1/2 times the square root of 2 over 5 times the integration of cosecant theta d theta. Now, because cosecant is a simple integration, we can just write it in terms of that integrand. We're now going to be putting it in terms of x, so we need to set theta equal to the secant inverse of the quantity square root of 5 over 2x plus the square root of 5 over 2. Now I'm going to put that in for both areas where theta is, and then we will have this as the final answer. Technique 8, roots elimination. Like with the last technique we covered, we will need to combine algebra with calculus. We will mainly be using u substitution with this technique as it is the most helpful. Suppose we are given a complicated polynomial where the degree of x is a fraction, let's say x to the 1/5. It is much more straightforward to integrate this if the degree of the polynomial is a whole number. How can we then turn a fraction into a whole number? Consider what is the smallest multiple of the denominator of the fraction, then multiply the fraction with it. So for example, let's set x is equal to u to the 5th. If we then have u to the 5th to the 1/5, that equals u. We can then use this for manipulation in our integral to simplify an integration. If there's more than one root or polynomial involved in the integral, we use the least common denominator, as we will see in the following example. We're now going to do an integration using root elimination. We have the integration of dx divided by the cube root of x plus square root of x. Now we're going to set x equal to u to the 6th because 6 is the lowest common denominator between 1/2 and 1/3. Plugging these values into the integration, we'll have the integration of 6u to the 5th du divided by u squared plus u to the 3rd. Simplifying this, we will have the integration, 6 times the integration of u to the 5th du divided by u squared times the quantity 1 plus u. We can then simplify this further to this integration. We then need to use a u substitution, so we're going to set z is equal to 1 plus u. That means dz will equal du. We then need to rewrite the integration, and it will look something like this. Now factoring it out, we'll have the integration looking something like this now. We then need to integrate part by part after we simplify. We'll then get 6 times the integration of z squared minus 3z plus 3 minus 1/2 z dz. We can then integrate term by term. Let me put that in there real quick. And we need to remember to put the plus c at the end. Now simplified, we'll have 2z to the 3rd minus 9z squared plus 18z minus 6 ln of z. However, the integration was in terms of x, so we then need to plug our u value and z value back into the integration or problem now, so that we have it in terms of x. Now write that out. And it should look something like this once you plug your z and your u values back in. And this will be the final answer plus c. In the end, why does it all matter? Integration is a foundation for many useful things, both in mathematics and in life sciences. Even though we introduce the subject of integration simply as an inverse of differentiation, the application of integration is pretty diverse. For example, of areas like physics, you can integrate the acceleration and find the velocity of an object. You can integrate the velocity of an object and find the position. You can also use integration in work, momentum, and center of mass to find those values, being very helpful. Further areas of integration in math that are helpful are areas under a curve, the arc length of a curve, surface area and volume of a solid rotated around an axis, and volume of a solid with a known cross-section. This concludes our Chapter 5 presentation regarding integration techniques. Hope you enjoyed, and that you're still listening. Mosh, give us a good grade, please.